All right, so hello everyone. Welcome back to your 12th and final Comp 335 tutorial. So this is the last tutorial of the summer semester. I'd like to start off just by saying that it's been a pleasure serving as your tutorial for this summer semester, and I hope it was somewhat useful. So with that being said, just quickly, if you hadn't noticed, the marks for assignment 3 have been posted. Maybe just a general comment about assignment 3, which the average is actually a bit lower than the previous assignments, and most of that weight has to do with the pumping lemma not being very well understood. So, for instance, and one of the sort of major or main mistakes that students were making, which was quite unfortunate because we really stressed on this point a few times, was that a lot of students were picking something like W is AAABB. So they were picking specific strings, and so there wasn't essentially a function. The length of W wasn't a function of M. So the average, I don't have it with me right now, but I think it was, actually I do. It was 61. So the average was 61, which is quite a bit lower than the other two. So so don't be too discouraged about the grade. It's of course relative, but just for the next assignment, make sure that something like this is well understood. And so for the question about tutorial 11, we can maybe talk about that at the end of the tutorial. Okay, so and then also if you hadn't noticed, the due date for assignment 4 is extended, so that's why I didn't post the tutorial video ahead of time, because we're actually going to have some time to cover Turing machines tonight. So okay, so it is, so maybe, okay, let me hammer this point home. It is never correct in a pumping lemma proof to pick a specific string whose length is not a function of M. So even if you showed that for that string it doesn't work, your pumping lemma is basically not useful. It doesn't show anything because it needs to be the length of W must be a function of M. Okay, so this is a prerequisite for any correct pumping lemma proof. Okay. Okay, so Turing machines. What is a Turing machine? So, and what's the motivation behind a Turing machine? So the Turing machine is essentially the most powerful computational device or machine that we're going to see in the course. And the reason for that is because you'll see in tonight's lecture that you can do basically everything with a Turing machine. So a laptop or any computer, any supercomputer is just one giant, like enormous Turing machine. So that's the reason why the kind of the culmination of the course leads to the Turing machines, because, right, so you'll remember we have the languages accepted by DFAs, which is the same as the languages accepted by NFAs, right? So for instance, L A star, that's in here. And then we have languages where the fact of remembering the last symbol isn't enough. So this is basically, you have no memory. right? So this is, you have no memory. Here, in the next kind of layer where it's the languages accepted by, let's say, because PDAs, you know, you have to be careful about NPDAs and DPDAs, but let's say it's the languages accepted by NPDAs, that's the same as the languages accepted by or generated by context-free languages. So this is, you have some memory. So the memory is, as you know, a stack, right? And then there are languages here. So here we can accept AN, BN, but there are languages here which cannot be accepted by PDA. So for instance, AN, BN, CN, that is a perfectly valid language, but cannot be accepted by a PDA because you can show that with the pumping lemma, right? So you can get contradictions for every case using the pumping lemma, okay? So that's where the motivation for a Turing machine comes. And a Turing machine basically has, as memory, it has a standard sort of tape. So it uses a tape as a memory, and this essentially is all you need to have really every kind of computational expression that's sort of that can be computed with a Turing machine, thanks to the fact that it's using a memory, a tape as a memory. Okay, so what do I mean by tape, and what does a Turing machine actually look like? So let me quickly go over the sort of mathematical definition. So a Turing machine M is defined as a 7-tuple, where you have a lot of familiar faces. So basically, like a PDA or a DFA, you have your actual state or sort of state diagram, where you have your initial state, right? Then you have a bunch of transitions, you have states, which belong in your set of states. Each of the states transition from one to another by reading a letter of your alphabet. So you have your alphabet sigma. The transition function is again defined as delta. You have your initial state, your unique initial state, and you have a set of final states, right? So you have your set of final states. And then to that is added some more interesting kind of memory properties, very similar to how we added things for PDAs. So we have gamma, or capital gamma, which is our finite set of symbols on our memory tape. So basically what you have to think of the tape is being an additional part of your machine where things can be written, where things can be read, and where things can be written, okay? So you have your input tape here. And together, this forms an actual Turing machine, okay? So the way your input tape works is basically you start with your input string. So let's say your input string was A, B, B. Then everywhere else on your input tape, you're just going to have blanks, right? Makes sense? It's just like how you have a text file, you have your string, and everything else is just blank, right? So you need a symbol for a blank space, which is usually just a square. It could be anything really, but that's the convention, okay? And you start your transition, your initial state starts at the very first symbol of your input string, so Q0. And so basically your input tape is going to be used both to read, right? It's going to be used both to read and to write things. So you're using this as a way of kind of navigating through a memory, okay? Okay, so that's a good question. So, and then maybe another note about your input tape is for a standard. So I just like to mention that this is a standard. So for a standard Turing machine, you can, once you read, let's say an A, there are only two possible moves that you can use. You can either go left on your input tape or right on your input tape, okay? So the stay option, which someone asked about, is not for a standard Turing machine. So it's for Turing machines which are a bit more sophisticated, which you'll see also a bit tonight. But for the assignment, please only use left and right. So because in the assignment, we're asking for a standard Turing machine. Okay, and maybe two extra notes. For final states in Turing machines, the convention is that you have no outgoing states for your final state. So if you have something like you read an A, so what happens is when you read something in a Turing machine, you write at that spot something else. So let's say you read an A, you write an A, and you go to the right. If this leads to a final state, then there should not be any outgoing transitions from there. Okay, so in other words, if you have a double circle, no outgoing edges. That's what that means. And a Turing machine halts in a state if there are no applicable, transitions. So very similar to your standard FA or standard PDA. Okay, so now let's look at an example to make this a bit more concrete. So I have this Turing machine here. So it's this Turing machine which is working alongside an input tape, right? And here I have a Turing machine which I claim accepts the language ABAN, right? So ABA to the N so any number of A's, right? PDAs do so. This is a convention just for Turing machines. Oops, sorry. This convention is only has to be forced for Turing machines where final states don't have outgoing edges. So it's fine for PDAs and for FAs. But so here we have a Turing machine, and here my input that I'm going to test out is going to be ABAA. So as I said, when you have an input string, now it's not just going to be me kind of putting arrows on the symbols. The actual input string is going to be, so this is the assumption, is the input string is going to be on an input tape, okay? So you have your input tape here, which contains your string W, okay? And like I said, your initial state always starts at the first symbol of your string, all right? And now we can just follow, let's see what happens when you feed ABAA to this machine, okay? So you start at Q1, right? And Q1, the transition says that if you read an A, then write an A and go to the right. So meaning if you're at Q1, right, which you are, and you're reading an A, then read that A and then write another A. So basically, you can just say that nothing happens, right? So nothing happens to the actual piece in the sort of the actual place in the tape, other than the fact that now the instruction is good to go to the right. So now you're going to go to the right. Now you're going to be in state Q2. Okay. So now you're in state Q2. So now what happens? You're in state Q2, and now the transition is if you read a B, then write a B and move to the right. So that's what I have here. I'm in Q2. I'm reading a B. I'm going to write a B, so nothing happens, and I'm going to move to the right. So I'm going to move to the right, and by moving to the right, I'm also going to land in state Q3. Okay, so now I'm in state Q3, right? Q3 is at the part of the tape where you're reading an A. So that means that I can use this transition that I'm reading an A, I'm going to write an A, and I'm going to go to the right. So I'm going to go to the right. So now my Q3 goes here. And then again, I'm going to use the same transition, right? I'm going to read an A, write an A and then go to the right. So my pointer moves to the right and I transition back to Q3. So I'm back to Q3, but now I'm no longer reading an A. Now I'm reading a blank, and the blank tells me that I finished reading my string, right? So what that means is that now I can use this transition, which says I'm reading a blank, I write a blank, and I go to the left. This just FYI, it doesn't matter. It could have been left or right. It doesn't matter where you finish in terms of your pointer. It just matters that you finish in a final state. Okay, so here I finished in a final state, right? And so my input string is accepted. So then you can notice that any input that looks like an A, then a B, then any number of A's will be accepted. Okay, so that's why we were claiming that this is the language accepted by your Turing machine. All right, so maybe just quickly an example of where the computation fails. So although here it, oh yeah, okay, sorry, I got confused. So here the computation should fail because you have AA, BA, right? So you have, so this doesn't match with your definition, your language definition. Okay, so does that actually happen? Well, you start in your initial state Q1, so you're reading an A. So this tells me again, if I read an A, then I write an A and I go to the right. So my pointer goes here. But now once I'm in Q2 and my pointer is looking at A, I don't have a transition, right, for when I have an A. So then my machine will halt. And because I'm halting in a non-final state, right, because I'm halting not in here, but I'm halting here, then I reject. Okay. Okay, so that is an overview of Turing machines. Can you move left or right more than once for, no. So you can only go, that's a good question. So you can only, once you have a transition, your pointer can only move exactly once to the right. So one space right or one space left. Okay. Okay. So now the next kind of thing to think of is, okay, so now I know how a Turing machine more or less works. How can I design a Turing machine to accept a language? So that's a very good question. For instance, let's look at ANBN. So it's very similar, my process of creating a Turing machine is very similar to the one of PDAs, which is first think of how you're going to use your memory. So in this case, think of how you're going to use your tape. And then once you're clear on the logic for that, then actually write your machine. Okay, so here, imagine you want to create a Turing machine that accepts A and BN. So in other words, if you have something like A, B, 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 right? So I have blank, I have A, I have B, 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 I have another blank, then this should be accepted. Okay, so what's the idea? How can I do this? Essentially, what I want to do is for each A, mark a B, right? So for each A that I have, mark a B. And then if I keep marking and I actually have the same number of A's as B's, then once I finish this computation, then if I look at all of my, if I look at the final string, then all of my symbols should be marked, right? So I shouldn't have any, right? So if I have more A's than B's, then I'll have some here that aren't marked. And if I have more B's than A's, then I'll have some here that aren't marked. So the idea is to mark your symbols so that you're sure that this tells you that you have the same number of A's as B's. Okay, so that's the idea. Now, how do you do this? Well, the other kind of distinction to notice is that you want to differentiate between marking an A and marking a B, right? Because you don't want to be you don't want to end up with the situation where you've marked everything, let's say you've marked everything with the same symbol. Okay, so actually showing it like this, you'll probably think, oh, well, why? So if I show it in this way, it's maybe a bit difficult to see why you need two symbols to mark the A's and the B's. And so it's more clear to understand that if you actually look at implementing that in the Turing machine. Okay, so that's what I'm going to do. So I know the answer is already there, but I'm going to do it myself just because I think it's a bit more helpful when I do that. So, right, so everything starts at Q0, right? Let's say here, say I have A, B, B, B. I have a blank, so I start at Q0 here, okay? And so what should my Turing machine do? It should see an A, right? It should see an A, and then let's say mark that with an X, okay? And then it should go all the way to the right and find the first B, right? So you see an A, you mark that with an X, and you go all the way to the right to see your B. So you go to the right, and now all of your A's, you can skip through them. So you say, if you see an A, then write an A, then go to the right until you see a B, right? So once you see a B, then what you'll need to do is you'll need to write a Y and go to the left, okay? So notice I'm going to use a different symbol for B, okay? And the reason for that is because once I finish marking my A's and my B's, what should happen is that to know that I'm done, when I go back to Q0, right? So here, let's say I read a Y for the B, and now I want to go back. I want to go back to find my next A. So to do that, I'm going to go back through my A's, right? I'm going to go to the left. And then once I see an X, right? Once I see an X, then that means that I went one step too far, and now I'm going to go back to my first A. Okay, so the A that's not marked. So that's what I'm going to do here. And so here in your Q0, right, your Q0 is actually the main sort of functionality that's going to be marking A's and B's. And so to finish, you need to essentially finish by seeing a Y here. So once you see a Y, right, so once you finish marking the A's and the B's here, then you should see a Y, then you can replace your Y with a Y and go to the right. Make sure that all your Y's have been marked. So essentially you want to check that you have all Y's here and that there isn't an extra B. And to do that, you need to check that the very last thing you see after going through all your Y's, which are the markings of B, is an empty or a blank symbol. So then the blank symbol can just be replaced by blank, and you can go to a final state. So of course, I'm sure, or I'm hoping that a lot of you are thinking that this Turing machine is incomplete, because it is. Because right now what's going on is I can mark the first A, right? So I can mark this A with an X and this Y with a B. Then I can go back, right? So I can go back here, then mark this A with an X, then go through here. But now I can go through all my A's, but then what's going to happen is I'm going to fall on a Y, right? So the idea is I actually have to also go through my Y's. So that's why here, I'm going to add a transition here that not only do I want to go through all my A's, but I also want to go through all my Y's, right? So this has become a mess, but let's do this again. So I have A, B, B, B. So I've marked this with an X, I've marked this with a Y. Now I've gone back, marked this with an X. So now I need to go through all my A's and then all my Y's to find the next B, okay? Which is what I'm going to do, right? So this is what this does. Then I'm going to find my B here, okay? And then the same idea is to go back, right, to go back now, not only do I need to go through all my A's, but I also need to go through all my Y's, right? So here, let's say I just went through this transition, right? So I read a B here, then I replaced it with a Y, and now I went to the left, so now I'm here. Now I need to go through all my Y's and then all my A's, right? So in addition to A gives you A and then go to the left, you should have Y gives you Y and then go to the left. Okay? And then once you do that, then your cycle is complete because now you can go back to find that X, then go to the right, mark that A with an X, then go to the right, mark that B with a Y, go back to the left. You see your X, so you went one step too far, then you go to the right, but now instead of a B, you have a Y, right? Which is not something you could do if you were marking X's everywhere, right? So you need to notice your X, because here you need to notice your Y, not your X. So now you notice that you have a Y, so you're going to go through all of your marked B's, and then you want to make sure that there isn't a sort of dangling B here, and that's ensured by this final transition. Okay? So that's the idea behind this Turing machine, right? And then there's some, yeah, so there's a computation, but I don't think it's relevant to sort of go through it because we just did, but maybe quickly, right? So you have A, B, B, right? So this gets marked with an X. So then you move to the right, you move to the right again, then you mark your B with a Y, then you go back again. You see, oh, you went one step too far, so then you go back to the right. Then you see, okay, now I have an A, so I'm going to replace that A with an X. Then go through your A's and your Y's to find your next B, right? Then you get to your B, you mark that with a Y, you go back, then you see you have an X. Okay, that means you went one step too far. So then you go to the right, ups, but here now, instead of having an A, I have a Y, meaning that I finished writing all my A's, right? So now what I'm going to do is I'm going to go through all of my Y's to make sure that I don't have any extra B's, which is what I'm doing here. And so then with this final transition, right, this final transition here, here, I'm reading a blank, I'm replacing that with a blank. Here right, it could have been left or right, but here I'm just going to the left and I'm ending in a final state, which means that I accept. Okay? So any questions about this? No questions. Okay. Right. So yeah, I'm not going to go much in detail with this, but basically the idea is like in PDAs, you have instantaneous descriptions, which are basically just there to give you a description of a full description of your Turing machine state with a single kind of in a single form, and that just looks like in this case the instantaneous description for Turing machines is the state you're at, what you've read so far, or basically, yeah, so what you read so far, or what's at the left of your input tape, and then what's at the right of your input tape. Okay, and then to describe a transition, like for instance, if you say here, if you're in Q1, and you're reading AK, then replace that with B and move to the right, then that just looks like, okay, I'm going to move Q1 here. So I'm going to move Q1 here. So now Q1 becomes Q2 here, and AK was replaced with a B. Okay, so that's how you read those. Okay, and then this is just to say that it allows you to create a definition of what the language accepted by the language accepted by a Turing machine is. So it's essentially all of the strings, and here notice lambda by convention is never accepted by Turing machines. Okay, So because it kind of defeats the purpose of a Turing machine, right? We don't really care at that point about an empty string. We're just focused on non-empty strings, okay? So then the strings accepted by your Turing machine M are all of the strings W in your alphabet, or over the languages, over the strings, over your alphabet, such that you start at Q0 and you have W on your tape. And with 0 or more moves, you can move to a final state. And here, notice that the content, very similar to a stack, the content of your tape is irrelevant as long as you've finished in a final state. Okay. All right. So okay, I thought there was an exercise for you guys to try out. Okay, but this is basically the instantaneous description, just making sure that it's understood. So I'm not going to go through all of it, but let's look at this transition. So this transition, what is this saying? It's saying that on my left, I have an X, then my cursor Q2 is pointing to A, and then after the A, I have YB, okay? And so what that means is I'm at this transition, I'm at this state, and I need to use this transition, right? So that means that I'm going to go, this is telling me that I'm not going to change my A, but I am going to move my cursor to the left. So meaning that my cursor is now to the left of X. So I have Q2, X, A, Y, B. And my Q2, right, I haven't changed state. I stay at the same state. Okay? So Derek, how would it look like if it were only a single variable? Not quite sure what you mean by single variable. Even amount of A's. Oh, okay. You mean a single symbol, right? Like a singleton alphabet, like this. I'm assuming that's what you mean. And I mean, in that case, it doesn't look any different, right? So it doesn't look any different from your typical instantaneous description. It's just that now it's just a bunch of A's, and let's say you have state Q3, and then you have a bunch of A's. If you have, let's say, Q3, reads an A, writes an X, goes to the right, goes to Q4, then that would just look like you have A. This A gets written as an X, and you move to the right to Q4, right? So that's what that would look like. So it doesn't really change, the size of your alphabet doesn't change anything. Okay? So now an exercise for you, so which of the following strings are accepted by the following Turing machine? So I'll give you a minute, and then we'll look at it together. Okay, so let's look at this together. So it looks like a few of you already got it, which is nice. So let's go through each string. So I have AABA. If I have AABA, then I'm going to start at Q0. I'm going to read an A, and so that's not going to work. Right, okay. So I'm at Q0, then I read an A, so I go to Q1. But now I'm stuck, right? Because at Q1, I don't have a transition for A. So this one just gets stuck, right? Then I have the next string, BBBA. In this case, if I have BBBA, then I can take this path here. I can read a B. So I have Q0, I read a B. I go to Q4. Then in Q4, if I read a B, I go to the right, stay in Q4. Then again, I'm going to read another B, go to the right, stay in Q4. Now I have an A. If I have an A, then that means that I can read my A here. I replace it with A and go to the right. So I go to Q5, and this is Q5 is a final state, which is excellent. That means that this is accepted. Okay. Then the next one, A, B cube A. So if I have an A, right, so I have A, maybe A, then you can probably see that I'm just going to get stuck when I read an A here, right? Because I'm going to read an A, read 3 B's here, but because I'm always going to the right, basically this just is for now acting like an FA. So if I go to the right, in this case, because I don't have a transition, then I'm going to halt, right? I'm going to get stuck. So this is a reject. And then A, B, B, I read an A here, then I read a B, another B, and then at that point, because I'm always going to the right, I end up at a at a blank symbol. So then I can transition to a final state. And again, because I'm at a final state, I accept. Okay?
Sir?
Yes.
So in this, for the Turing machines, there's no concept of having to consume all the symbols, as long as you're in a final state, regardless of how you got there.
Yeah.
Even if you technically haven't read everything, it's
Yeah.
still accepted.
Excellent. Yeah, that's a very good observation. So keep that observation in mind for this next question. So it's the same Turing machine, but now what is the language accepted by the following Turing machine? Okay. And so you just got a very nice hint. So I'll give you 30 seconds to think about it. Okay, so very good. I see. Okay, I was trying to fool you with this question, but so let's look at it. So here, I hope sort of logically you can see that there's basically two languages union that are going to form the language accepted by M, right? Just because you have two branches in this case. So in this case, that's quite easy to see. So in this case, you have the language accepted by sort of this part here, which is just I read one A, then I can read any number of B's, and then as long as I end, right, I end with any number of B's, it can be none, then I'll have a blank, and I can move to my final state, right? So that's why I have L of A, B star. Union, for my other branch, I have to start with a B, right? Then I can have any number of B's, so B star. and then I can have an A, right? But if you do something like this, right, then that's not correct. That's not entirely right, because if you have something like B, B, A, B, what happens is you start at Q0, then you go to Q4, right? So you're at Q4, then you move to Q4 again. So now you're at Q4 and you're reading an A, so then you move to Q5. So it doesn't matter that there's something after. In fact, it doesn't matter what's after here. It could be 100 more symbols. It doesn't matter because you're in a final state. So the concept, as someone said very, very wisely, the concept of fully reading your string isn't necessarily implemented here. There's nothing that forces you for that to happen. The only way to force that is if you're finishing everything here with a blank. Okay, so that means that here, not only is it B, B star A, but it's B, B star A, or B star. Yes, it is confusing, which is why I wanted to show it. But for Turing machines, right, if we go back to the definition, it's sort of, it should be, well, not clear, but you can kind of see why the definition allows this, because here it's saying you're reading W, you go through a bunch of operations, but it doesn't matter if whether or not you read W, right? So as long as you end in a final state. So maybe this is like the first symbol in W, and this is the next 10 symbols in W, it doesn't matter, as long as you end in a final state. Okay? All right. So so far, not much of this has been very helpful for the assignment, so that's why we're going to do that now. We're going to look at designs of Turing machines, and I think what I'm going to do, just because I want to show operations as well, I might skip the next one. So I'll give you, well, okay, first, okay. What's the idea here, right? So let's first go through what the idea would be. The idea here is you want to accept a string AN, B2N, CN, right? So something like AA, B, 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 C, C, okay? So then the idea is for each A that you read, mark it, let's say with an X, then mark the corresponding two B's with another symbol, because for every A, you need to see two B's, so you mark two B's, and then for every two B's, you need to see one C, so you mark a single C with a Z, okay? And then you do this loop back and over, right? So you keep doing this until you get something like X, X, Y, 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 Z, Z. Then once you reach this point, you can go through your string, make sure that you haven't missed anything, right? Make sure you don't have like a dangling B here. And then you should be able to get to a blank symbol. Okay, so that's the idea. Okay, so now I'll give you, let's say 2 minutes to try to think about it. And we'll look at it together. All right. So hopefully you had a little time to think of this question. I kind of understand that it's not immediately obvious, but let's try to go through it. So I'm basically going to use what I just wrote here as my template, and just basically go through my transition diagram, filling up the things that need to be filled up. So here, what I need to start with when I start at Q0 is I need to start with an A, right? So I start with an A, and I'm going to mark that A with an X. Then I'm going to go to the right. So I'm going to go to the right all the way to my B's. And to do that, I just need to read A's, write A's, and go right. Right? So I'm going to leave some, this isn't going to be a complete Turing machine, like it's going to have some transitions missing, but this is the way I like to do it. So I read a bunch of A's until I see a B. So once I see a B, I'm going to mark that B, go to the right, then again, mark that B with a Y, go to the right. Then I should keep going through all my B's until I end up seeing a C, right? Once I see a C, I'm going to mark it, let's say with a Z, right? So here I have X, Y, Y, Z. So at that point, once I'm here, I'm going to start wanting to go to the left, right? So I'm going to want to start going to the left. So I'm going to go left here, and then I'm going to go back, right? So I'm going to go back all the way until I see an X, right? An X, meaning that I've gone one step too far. I'm going to go back to the right. So to do that, I need a transition here that allows you to go all the way back. So I need to read through my B's, through my Y's, and through my A's, right? So I'm going to read through my B's, through my Y's, and through my A's. Okay, then I'm going to go back here, right? Now I'm at Q0. I'm going to again read an A, write an X. Then I'm going to go to the next kind of transition. So I'm at this transition, but my pointer is here. So what I need to be able to do, as well as to go through A's, is also to go through Y's, right? It makes sense. So I'm going to also go through my Y's, okay? Until I hit 2 more B's, so I hit 2 more B's, okay? Then once I hit my 2 B's, I'm going to go through all of my other B's, right? Maybe there's some more here. And then once you've gone through all your B's, then you hit your C's, right? So you're at your C. And you do the same thing. You write a Z, you go to the left. Here, you don't need to change much, right? So you don't, right? Like you don't need to add, let's say Z's here, it's taken care of. So you go through your B's. Well, in this case, yeah, so here you would go through your B's. Okay, this is not clear because just give me 2 seconds, let me clean this up. Right, so you have A, B, 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 C, C. So this is marked with an X, X, Y, 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 Z. Okay, so now I just marked this C with a Z. I'm going back to the left. Oh, okay, so actually I didn't make, there should be an extra transition, and that extra transition should be, oh no, actually, okay, no one's saying anything, which is worrying because, yeah, okay, thank you. Yes, so, okay, yeah, there's a transition missing for the Z's. Okay, so there's one missing here actually because that's what I just noticed. If I'm going through my B's, I also need to go through Z's here, right? So I'm also going to go through my Z's here to the right, okay? So that means that here I need to go through my Z's, then maybe some more B's, then the Y's, and then maybe some A's. Okay, very good. Good. So you go to the left, and then Once you've gone through, let's say, the last A, you'll hit an X. And then once you hit an X, you'll be back here. But how do you know you're done? Right? You know you're done once you have nothing more to write here, right? So you have nothing more to write for your A's, meaning that you have a Y right in front of you. So if you have a Y right in front of you, write a Y, go to the right, okay? Then go through all your Y's, go through all your Z's, right? So this step is actually very important because it's checking that there isn't something like an extra C somewhere, right? That you might have missed. So then go through all your Z's, and you know that you have a matching pattern if at the end you're reading a blank symbol and going to the left. So then you can finish in a final state. Okay?
Sir,
Yes.
is it possible to put Y to YR and Z to ZR together? Because we already discussed about the order in the top of the graph.
Yeah, that's a good point. Yeah, you could also, yeah, that's a good point. Because you've essentially dealt with the ordering here, you could also, just to make your TM a bit shorter, you could put the Y's and the Z's at the same place, because you don't need to be concerned about having a Y, a Z, and then a Y, because that would have been taken care of. Your machine would have already halted somewhere here. Okay, so yeah, that's a good point. Is that what I do here? No, okay, but it could be, right? I could shorten this for that to be right. Yes. All right. Any other questions about this? So basically, hopefully now you kind of see at least the mindset of how to write a Turing machine. So now, like if I gave you something like AI, say BJ, I different from J, right? Then you should think of basically what's the idea in terms of having a tape, right? So if I have, let's say, 3 A's and 2 B's, right? Then, well, the idea here is just you want to essentially have some excess, right? So you can basically do the same operation that I did here, but then just have some excess, let's say X, Y, X, Y. And then once you're done that, then you can detect, right? So if you read it under X, and you notice that, oh, actually you have a blank, then, oh, in fact, that's actually very good. That means that you're going to accept. Okay, so then something like that, right? Or something like, I don't know, A, I, B, J, or something that's not context free. So yeah, so like CK, I strictly greater than J, strictly greater than K, right? So here you just need to make sure that you're marking less A's than B's, and make sure that you're marking less B's than C's. Okay. So once you get the logic, hopefully it's a bit more easier to understand how to make something like this. Okay. So, all right, good. So now let's do one where I don't explain what the logic is. So in this case, we want to accept a Turing machine, We want to create a Turing machine that accepts the language WCW, where in this case, I'm helping you out here. I'm giving you the C, so you don't have to find the middle of the string. C is marked by the middle of the string, and W is just A's and B's. Okay, so I'll give you 2 minutes, and then we'll look at it together. All right, so maybe we just quickly address Turing machines cannot be, well, a standard Turing machine, and the one that's asked for in the assignment must be deterministic, so it can't be non-deterministic. And yeah, so the other question is this. I mean, the exercise was just to design a Turing machine, doesn't ask, it's context-free. But actually, yeah, so the intuition there, this, honestly, I haven't checked, but I don't think it's context-free, because if you have something like WCWR, then that's context-free because, right, you know how a stack works, when you push W, when you push your string, the last symbol of your string is at the top of your stack. So if it's WCW, then there's no real way, right, with a stack. You'd have to use two stacks. You'd have to stack your W, right, and then put it back in another stack, and then compare with W. And so that's obviously if you're using more than one stack, then that's not a PDA. Okay.
Sir?
Yes.
Like if we remove, okay, so for example, if A go to X and B go to Y, and
Yeah.
then in the another state, for the second W, when we remove A, okay, so if we remove Y with A and then X with B.
Yeah.
So
You're describing WWR.
no, I
right?
mean like WCW. So you said it is not context free?
I don't think it's context free.
Yeah, but like what if we make a PDA
Okay.
which is,
So let's say you have A, B, B, C, A, B, B. Okay, so how does your stack work?
so like, okay, so X, Y, Y. Of course,
Right.
there is a
So
dollar
X,
symbol
Y,
on the
Y,
bottom.
yeah.
Yeah, and then if we remove,
No, but you can't remove.
oh,
Yeah,
it
once you
doesn't work.
remove, you can't get it back.
Yeah, true. Okay,
Yeah.
yeah. Okay, thank you, sir.
Yeah, no problem. Okay, so that's why I don't like you need to prove it, but I don't think it's context free. Okay, so then what's the idea here, right? What's the idea? WCW. Let's say you have A, B, B, C, A, B, B. Well, the idea here is a bit, well, it's different than the other example. Here you can actually use the same element to mark your A's and B's, but you just want to make sure that you mark the same position with the same, you check the same position relative to the left and right substring. So in other words, what I mean by that is if you're marking an X here, then you should go through all of your string and then make sure that the first element or symbol of your second substring is also an A. And then if it is, then you can mark that and then go back. Then you see, okay, I have B. So now if I have a B, then that means that if I go through my string, I have to see a B and mark it X. And then you can kind of keep going. And at the end, you should have like sort of XXX, C, XXX. You should have something like this, okay? So how does that translate in terms of a Turing machine? So you start at Q0, right? Then there's two choices, right? You can either read an A, and so you're going to mark that with an X and go to the right, or you can read a B, mark that with an X and go to the right. So let's start with this branch. Let's say you read an A, you mark that with an X, you go to the right. Then you're going to want to go through all of your other, because I don't want to, okay, let's write it here. You're going to want to go through all your other A's and all your other B's, right? And then why I'm saying that it's a bit easier here, this machine is easier to write than for WW, because for WW, you don't know where the middle of your string is. Here, you know what the middle of your string is because it's delimited by C, right? So here, once you see a C, then you can say, oh, okay, now I know where the middle of my string is. So now I can go and I can now look for the corresponding A, right? So in this case, let's just say for now that we've marked an A. So we're just going to basically read another A, mark that with X, and then go to the left. So this isn't a complete Turing machine. Okay, so it's not a complete Turing machine. I'm gonna complete it. But so now what we have is we have X, B, B, C, X, B, B, and now I'm back here, right? So now that I'm back here, what I can do, and see here, this is why I was, okay, it's gonna be a bit messy. Okay, so then let's say here, I'm gonna read a C. So once I read my C, I can go to the left. So now I'm here. Then I can go back through all my A's and all my B's and then finish off, right? So if I read, so basically what I'm now looking for is to go one step too far, so then to find my X. And then once I find my X, I can go to the, I can write an X and then go to the right, okay? So then, so now that means that I have X, BB, C, X, BB, and now I'm back here. So now I'm gonna use this branch, replace the B with an X. So now I'm gonna go through my A's and my B's to the right. And again, I'm gonna find my middle thanks to my C. Then once I'm here, I actually have to go through an X, and it could be more than one X. So now because I've added it here and it's symmetric, right? Then I can just add it here as well. Okay. And then what I'm looking for at the end is a B. So then once I see a B, I write an X and then I go to the left. And then here, what needs to happen is I need to go through all my X's. and and then, right, so I go through all my X's, then I read the C, go to the left, go through all the remaining A's and B's, and then do the same thing, right? So then I would read an X, write an X here, then I go here, I write that X here. So now I'm here, right? I'm here once I've gone back to the left, so I'm here. I go through all the X's, then I go through C, then I go through the A's and B's, then I find an extra X, right? I went one step two back. So now I'm going to go back to the right and then repeat the process, right? So the idea is that once I'm done, then what I should see is just a C, right? So at this point, when I'm finished, then when I'm finished, when I go to the right, I should see a C instead of an A or B. So when I see a C, then I can go to the right. I can go through all the X's, right? And of course, I want to make sure that I don't have, let's say, an extra A here. So that's why I'm going to make sure that I have a blank. I can replace that with a blank. Let's say go to the right and end in the final state. Okay. So so that's how you write the TM for this guy. Okay. So I was going to ask any questions. It looks like someone answered a question. So looking for A's and B's, X. Yeah, exactly. Because here you don't want to differentiate, like you don't care about counting the A's and comparing the count to the B's. So yeah, that's why. Okay. So so hopefully now that helps for solving which question? For solving this question in assignment 4. Okay. So now I'm just gonna wrap up by showing you how you can solve a question like this. Okay. So and I can already tell that I'm just going to have time to do this exercise. So I'm going to do this one and then probably post this one. But I think this one actually might be a bit more relevant for the assignment. But basically, a Turing machine, you can use it for one, right? So a Turing machine, you can use it for one, accepting a language L, or you can use it two to compute a function f of x. Okay. Yeah, so I'll talk about that. I'll talk about that one at the end, because I was expecting that question. So compute f of x, right? So basically, you're given an input x as a string, right? So let me just show you. So you're given an input x where q0 is pointing at x. The idea is your Turing machine should do a computation f such that at the end of the computation, your final state, right? So once you're at your final state, you should be back at the beginning of, or basically what I'm trying to say is your final state should be at the position in your tape that points to the answer of your function. So it should be pointing at f of x. So meaning that if you have something like f of x is 2x, and let's say x is given in unary, so let's say it's just a bunch of ones. So then 2x here would be 8 ones, right? So 1, 1, 1, 1, 1, 1, 1. Then what that means is if you have your input is 1, 1, 1, 1, then your Turing machine should compute 1, 1, 1, 1, 1, 1, 1, 1. There should be blanks here, and your final state should be back at the 1 here. Okay? So that's the idea. So now let's look at how we can implement this idea. So we have f of x is equal to 3x plus 1. So suppose that x is given in unary. So let's say it's 3 ones. So the idea here is going to be the following. So what I'm going to want to do is, because I want to essentially, for each one that I see, I want to add an extra 2 ones, right? Because then I'm going to have 3 ones here, then an extra 3 ones here, then an extra 3 ones here, right? What I'm going to do is I'm first going to start with my ones, and let's say I'm going to mark them with x's. So I'm going to mark them with x's, and then for each x that I see, I'm going to add 2 ones, right? So then, and then once I do that, then I can remove this x and mark that x with a 1, okay? So then I'm going to do the same thing here, right? This x is going to be marked with a 1. I'm going to put 2 ones to the right. And this x is going to be marked with a 1. I'm going to put 2 ones to the right. And then, so now what I have is I have a 3, 3, 3, so I have 9. Then what I could actually do, which I don't do, but I could use the blank state as the extra plus 1. But this isn't right. Like if this was like plus 7, then that wouldn't help. So what I'm going to do at the end, I'm just going to process all of this and just add an extra 1 at the end. Okay, so that's the logic. So how do I do that? So imagine, right? So imagine I start with 1, 1, 1. I have blanks on the left and the right. So I have Q0. Okay. So what I'm going to do is I'm going to go through all my ones. So I'm going to pre-process all my ones. Let's say mark them with X's. So I have X, X, X. So now I have my blank state. So now I've reached, so the idea is to get all the way to the blank state, right? Get all the way to the blank state. And once I'm at the blank state, I'm going to do what I just described. So then for each X that I see, I'm going to go here. Or actually the smarter thing that I didn't do here, the smarter thing is I'm going to replace this blank with a 1, then the following blank with a 1, and then have, right? So because there's blanks everywhere on my tape. So then that's going to allow me to, for each X, add 2 extra ones. Okay, and that's going to be the flow. So to do that, right, So what I'm going to need to do is, so I've gone back here, right? So I've read my blank and I've written a blank and I've gone back here. So just not to confuse you, I have a blank here, I have blanks here. Okay, so so then I have an x, so I'm expecting an x. So then if I have an x, I can say, okay, I can write a 1, then go to the right. What I should have here is a blank. So if I have a blank, I write a 1 and I go to the right. And then I should have another blank here. So now I've written another 1. So now I should have another blank here. Okay, and then I should write another blank with a 1. And now I want to actually go back to the left, right? So I want to go back to the left. So I want to find my next x. So I'm going to go back all the way to the left. So here is the next, or actually I think I wrote an extra 1 here. So this should be a blank. This is the one that I just wrote. Now I'm going to go back. Here I wrote a 1. So this is a 1, this is a 1, this is a 1. So I'm going to go, or the idea is that I should be able to go through all my 1s until I see another x, right? So that's what I'm going to do. I'm going to go through all my 1s to the left until I see another x, right? So, and then once I do see that other x, I'm going to go here. I'm going to write that x with a 1. Then, so now here's the caveat is I need to add an extra 1 here, transition, because that wasn't necessary before, but that's going to help me to go through all my 1s here. Then I'm going to add 2 extra 1s here and then go back, right? Then I'm going to write a 1 here instead of the x, go back here, okay? And the idea should be that I go through all my 1s. So what's the idea is that once I finish replacing the x's with the 1s, I should just see a blank. So then here, if I see a blank, that means I'm done writing the sort of 3x. So I finished this part. So then to do the +1, what I'm going to do, well, the way I did it here is that what I'm going to do actually is I'm going to replace this blank with a 1, right? So replace this blank with a 1, go to the left. So now I'm here. And remember, the last thing you need to do is you need to make sure that your pointer is pointing at the answer of your function. So here, the answer of my function starts here. So that means that here, it's actually quite important where I finish. Here, in this case, I'm going to use, because now I'm here. So I'm going to use a blank, write a blank, and I'll go to the right. And that can be my final state because now I'm actually pointing at the answer. So I have a 1, I have 3 1s, another 3 1s, another 3 1s. So I have 1 plus 3 times 3, which is 10, which outputs the given answer of my function. Okay, so so then hopefully that's more or less clear. I don't know, are there any questions? No, not ruined. Because now, if you look at this question, actually both of these, right? Like, right? So this is, okay, like, come on, guys. Like, I mean, I kind of, we picked this example on purpose, but this one might be a bit harder because here it's like you're having, this is both a function of n and m. So for this, just kind of, right, just think of it as a for loop. In my head is for each one that you see here, copy all of these ones, right? And then just do that n times. So that's the logic, okay? Okay, so then, okay, there's actually a question. Why you replace a blank? Yeah, So the reason here that I replace a blank by 1 is because it's 3x plus 1, right? So then, so I've done all of this. All of this is my 3x. Now, I know that I've finished doing my 3x here with this machine. Then I can add a 1, and actually, like if this was like plus 7, then I could just add, let's say 7 blanks here with 7 blank gives you 1, goes to the left. So I could do that 7 times. And then do this move here, and then I would get plus 7. So the extra blank here is just to give you that plus 1. Okay? When we read this, we don't read the blanks. What do you mean by read the blanks? Yeah, so like when you start, like when your machine starts, you're assuming that Q0 is at 1, 1, 1, and you have blanks everywhere else. So your blanks are everywhere, so you can utilize the blanks so that you can, oh, okay. Mostly, so it doesn't, what's the alternative? I'm trying to, like, if this was 2x, right? So if this was 2x, let's say you had 1, 1, 1, then you could say, okay, for I have, for each 1 that I have in my initial x, I have an extra 1, right? So that's the logic here, right? So then it's the same logic if you have, let's say, 4x, is if you have 1, 1, 1, then for each 1, you're going to have an extra 3 ones, okay? So then if you do that for each, if you do that for each of the ones here, right? Because this, in my head, 4 times x is just 4 plus 4 plus 4, right? X times. So then that's what you're doing. You're doing this 1 time, then you're adding another 4 another time. You're adding another 4 another time. So that's the logic. Okay. Any other questions? So yeah, so like I said, I'm going to post this one because there's not enough time. No? Okay. So then, yeah, so for the assignment, so then I think, yes, I was, yes. Right, so hopefully this is clear how to do that. This is clear how to do that. Yeah, so to be honest, like the TA, the other TA and I, we also talked about this, and we're not entirely sure if it, like to be honest, I'm not sure if it is or if it isn't context free. But like my intuition for this question is, imagine you, right? So like I'm always thinking of it as, yeah. So because if you're thinking about it in terms of a stack, then your stack has to be like super powerful, and then it's not really a stack anymore. You kind of need some memory for that. So that's why we were kind of leading towards the other way. And so for the other way, I agree that the pumping lemma for this question, not very easy. I did, in your textbook, there is a question. There is a question in the textbook where you want to show that AI bj for a different than j is not regular. And so in the textbook, they give the proof for the pumping lemma for that one. And so I feel like it might be maybe useful to get some inspiration from that one. But again, This question is, in my opinion, pretty difficult. I don't have a very definitive answer, but one thing. So whatever you do, because this was very common in the last assignment, and we were very strict on this. Don't actually just give your intuition, because if you just give your intuition, we can't give you more than like 1 mark. So if you at least try the pumping lemma, try some things out, we can give you par marks. But intuition, really, that's not really enough. Okay. And then for Q5, I kind of described how you would do it just for, let's say, I different than j. So in this case, you have 3 of these, right? So you just have to find a way to repeat the same process 3 times. Okay. So that's my hint. All right. I actually need to go at 5:40. So any other quick questions? Yeah, yeah, the Turing machine is I'm expecting it to be like a page.
Sir, I have a question.
Yes, quickly.
When is your final exam review?
Yes, probably Sunday, sometime during the day. I'll send the Moodle announcement.
Okay, thank you.
Yeah, no problem. Okay, any other questions? I have a meeting in a minute, so. All right, so okay, good. So like I said, it was fun TAing the class. Hopefully you learned a bit, and have a nice final lecture. And I'll see for those of you who'd like to attend, I'll see you at the final review. All right, take care, everyone. Bye-bye.